So we already know what K equilibrium is. K equilibrium is equal to products over reactants. We also have something that's called Ka. Okay. Ka is the same as the equilibrium as products over reactants, but in this case we're talking about acids. Ka is called the dissociation constant. Okay, so for this reaction, H plus A minus, so this is the acid, here's the water, the H plus will go to the water, then you have the A minus left by itself, and then the H3O plus, which is the hydronium ion. For this reaction, if we wanted to get the K equilibrium, since it's an acid, it would be called Ka. So it would be A minus times H3O plus over HA. Okay. In this reaction, we can also write it a different way. So the way I've written it before and the way I will be writing in the future is this way. So you have the HA. I don't normally write the water. I just say that the HA dissociates into H plus, and I'm sorry, this would be the A minus, so it matches down here. Just erase this. It would be the H plus. I'm going to write that first to match. H plus and then A minus. Notice I just broke this apart, and that's what acids do. This is the same as this substance, and H3O plus is the exact same thing as the H plus, just a shorthand way of writing it. So, or Ka can also be written as A minus, or I'm going to write the H plus first, H plus times A minus. It doesn't matter which one you write first. It's just, it matches HA over HA. Okay, so what this tells me is that Ka is the ratio of the amount that dissociates over the amount that doesn't dissociate. Okay? So you can either write it this way, that's the equilibrium expression for the acid, or you can write it this way. They're identical. Okay, notice the A is the same, A and the A, the HA and the HA, the H3O plus is H plus, same thing. Okay, so this is the equilibrium expression, and the Ka is called the acid dissociation constant. Okay, so the greater the Ka, the stronger the acid. Okay, what that means is if this dissociates and then you have a lot of them, let's say if you have 1,000,000 of them that dissociates, and only one does not dissociate, and this is very small, then you have a very big Ka. Okay, so it says the greater the Ka, the stronger the acid. You guys memorize the top 6 strong acids, and they are high, clean your bedroom. This is how I memorized it. Clean your bedroom, BR for bedroom. So no clowns in the closet. Okay, so this is H2SO4. You have to memorize this. HNO3, HClO3, and HClO4. These are the top strong acids. If you look at their Kas in a chart, it will tell you that the Ka is very large. They can't even give you a number. The reason they can't give you a number is because the number in the numerator is so big and this number in the denominator is so small that it reaches 0, so it's undefined. It's just really huge. Therefore, we don't have Kas for these substances, okay? But we do have Kas for weak acids. As, for example, HF is a weak acid, and you can see the Ka right there. 6.8 times 10 to the negative 4, and so on. Again, here are some examples of acids. The H's, this is a binary acid. If it has oxygens or oxyacids, the H's are always dissociating from the O. Okay? And these are the Kas. I also would like to show you in your calendar, I've given you a link to the, over here it says Appendix D, aqueous equilibrium constants. If you click on that, it'll give you this reference sheet. This reference sheet is inside your textbook as well. It gives the acids by order of an alphabetical order, and it also gives you the Kas. Okay, as you can see, this acetic acid is vinegar, 1.8 E negative 5. You'll be using that one a lot. This one has 3 Kas, Ka1, Ka2, Ka3. The reason that is, can you guess why? Yes, because there are 3 H's that can be deprotonated. As you can see, the first one is fairly easy, but as you go further and further, if you take the second one, it's a lot harder than taking the first one, because when you take one H plus, it becomes a negative, and taking another positive from something that's already negative is not electrostatically feasible. It doesn't want to get rid of the second H, so it's harder. The third H is even harder to get rid of. Okay, so that means 3E negative 12 means there's very little of the third H coming off. Okay, so remember that the H plus attached to the O is the one that comes off. In this substance here, this H is not coming off because it's on the carbon. It's this H that's coming off. Okay, if Ka is large, that means it is a strong acid. If Ka is small, that means it is a weak acid. Acids less than 10 to the negative 3 is really weak. Okay, for example, HF is a weak acid. When you're getting the pH of something strong and something weak, you have to treat them differently. The reason is this. If I tell you that you have a 0.01 molar of hydrochloric acid, you know you're going to have 0.01 molar H plus and 0.01 molar Cl minus. So to get the pH, you just go pH equals negative log of the H plus, which is 0.01, and you have your answer. If you want to get the pH of a weak acid, for example, HF, if this is 0.01, you don't know how much of this you'll get. It's not going to be all of it breaking apart. It's going to be a part of that, okay, breaking apart. So you can't tell, therefore you can't do it easily as a strong acid. So I'm going to teach you how. How do you get the pH of something that is a weak acid? How do you know how much is coming apart? Okay. Before I do that, I'm going to show you how to calculate Ka if they gave you the pH. Okay, so for example, you have a beaker, and the beaker has 0.1 molar of this formic acid. So you have a 0.1 molar of HCOOH. Which H comes off here? Of course, it's the last one. And remember, this structure is a C double bond O OH. So this is the H that comes off. Okay? The pH, when you take the pH of that, it is pH, that's a pH probe, pH 2.38, it says right here. Okay? Find the Ka. Okay, first let's write an equation. The equation is HCOOH arrow HCOO minus plus H plus. Okay, the formula for Ka is H plus times HCOO minus products over reactants, HCOOH. So that's the formula to find Ka. Okay, so we have to use an ice box to get concentrations at equilibrium. Okay, once we get it concentrations at equilibrium, we can plug it in here, and so we can solve for Ka. So let's go ahead and start the ice box. So I have it here. Okay, so initially I have 0.10 and I have 0, 0 according to this. Okay, and it says the pH is 2.38. So that means when this has reached equilibrium, the solution up here has reached equilibrium, the H plus has come apart, and that pH that you get is already at equilibrium. So this is ice. Okay, so initially it's 0.100. This pH is already at equilibrium. So you've put the formic acid in water and you've waited a while. You took the pH, so you know this is at equilibrium. Okay, so if the pH is equilibrium, then you have to write here. Okay, first I have to want to fill this out. Since H plus proton transfer is very fast, the H plus, this happens very fast, breaking apart is very fast, the observed pH is already at equilibrium. Okay, so this concentration here has a pH of 2.38. To get the molarity of H plus, the formula is equal to 10 to the negative of the pH, which is 10 to the negative 2.38. Go ahead and plug that in the calculator, which is 0.0042. 0.0042, and again, that's at equilibrium, so these are equal. Because this is going to the right, so it'll be minus x plus x plus x. So you know that x is equal to 0.0042. So 0.0042 is what dissociated, so 10.1 minus 0.0042, which is 0.0958, is what's left over of the formic acid, intact formic acid. Okay, so if you wanted to get the Ka, all you have to do is plug in these numbers. So Ka is equal to H plus times HCOO minus divided by HCOOH, which is equal to 0.0042 times 0.0042 divided by 0.0958. And that will give you the Ka, which is equal to 1.8 E negative 4. That is the Ka of formic acid. Considering that, that tells me formic acid is pretty weak. Okay. You can also report the Ka in terms of how much ionized. They call that percent ionization. So what you would do is you see how much came apart versus how much came apart or how much ionized came apart as ions and how much didn't come apart. So for this you can just do the percent ionization would be 0.0042 is how much came apart divided by 0.1 times 100. If you wanted to report it that way, so you would go ahead and plug that in. 0.0042 divided by 0.1 times 100 is equal to 4.2% ionization. So what you can say is that, oh, if I put formic acid in a beaker, 4.2% of it will break apart, and that's how much H plus I'll get. Okay? Here's another example. If you have 0.035 molar HNO2 and it has that much H plus, so that's going to be 3.7 E negative 3 is how much H plus came apart. The initial is 0.035 molar. The percent ionization would be 3.7 E negative 3 divided by 0.035 times 100 would be about 11% ionization. So what that means is 11% of this number will break apart into H plus and NO2 minus. Okay, so let's do another example. It says that you have a 0.1 formic acid. It contains this much H pluses. Find the percent ionized. Go ahead and pause the video and try it. Okay, so easy, percent ionization is equal to H plus over HCOOH times 100. So how much broke apart was 4.2 E negative 3 divided by 0.1 times 100 is equal to 4.2%. Oh, I think we did that already. Is that the same as up here? Yeah, same. We already did that problem.